Polynomial functions. Yeah, 3.1. Let's analyze the word polynomial. Polynomial is made up of two words, polynomia and le. Okay? Polynomia and le. Not really. Not really. It's made up of two roots, poly and nomial. So what does poly mean? Parrot? Polly? Could be. It could be a name of your parrot, right? Polly want a cracker? I hate crackers. Got a chimichanga. That'd be a cool parrot. Poly means what? Where else have you seen the word poly? Polygon. What does polygon mean? Has what? Has like more than one side, okay? So poly means like more than, right? Like more than? And that's right. That's right. Poly means many. Poly means many. Okay? M-A-N-Y. Not Manny, like handy Manny. Like M-A-N-Y. So a polygon has many gons, right? Gons. Many gons. And of course, gons means what, I guess? Sides. Good. So polygon, many sides. So polynomial means many nomials. So what does nomial mean? Many nomials. Y'all know what nomenclature is? Like in science, you have your binomial nomenclature. Genus, species, Homo sapien. No? It's a structure by which we can name. There you go. So nomial means name, literally. But in our examples, nomial is going to mean not name, but terms. Okay? So a polynomial means a many-termed something, and we're going to be looking at polynomial functions. So we're going to be looking at many-termed functions. Now, the terms themselves, as you're going to soon see, have to be qualified. They can't just be like any term. They're going to have to be terms of a very specific type. So polynomial is a many-termed function, and of course, we know what functions are, right? They're fun, and they have passed vertical line tests, something like that. Now, let's kind of think back to Algebra 1. So we're going to squeeze something in right here. In Algebra 1, and I'm going to use the number 1 instead of the Roman numeral, I'll use the Arabic. You studied polynomial functions. They were of the form y equals mx plus b, right? Remember that? You could think of the 1 in Algebra 1 as being the exponent on the x. In Algebra 1, you studied what we call first degree polynomial functions, okay? So what is the degree? It's 1 because 1 is the largest exponent on your terms, right? And we've done this already when we were doing limits. Sorry, as x goes to infinity, we had to find the leading term. All right, so Algebra 1, we're looking at polynomials, mx plus b. Of course, m was the what? Slope. And b was the y-intercept, right? B for y-intercept. Makes sense. Right? Y-intercept. The b is silent, right, in y-intercept. But at least the m makes sense for slope, right? Yeah, it does, actually. Because it's the French verb for to climb a mountain. Monter, the mountain. Yeah. Slope, steep. Okay, good. Now, you graduated from Algebra 1, and you either A, took geometry, or B, went right into Algebra 2 because you love that stuff. Geometry can wait. And that's what you're told to do. So, Algebra 2, then, you kicked it up a notch, right? Kicked it up a notch. And maybe even started this at the end of Algebra 1. You were introduced to this. You then had a polynomial that now had the matching degree of the course number. It was Algebra 2, and you primarily studied degree 2 polynomials. Now, we call this one over here a first degree polynomial. And what did the graph look like of mx plus b? A line. So we called it linear. This one was now a degree 2 polynomial, and you called it a what? Quadratic, right? Right. It makes sense. First degree, linear. The graph is linear. second degree quadratic, right? Because quad means what? What, Blake Payne? 4. What the? Hang on. Degree 2 quadratic. Maybe you were just pronouncing it wrong. It should be like bidratic, right? Bidratic? Or didratic? Not quadratic. Maybe your teacher had it wrong and is just too embarrassed to tell you. No, I think it was published in the textbooks like that. Maybe the guy way back in the early days just didn't know the difference between 2 and 4 and he called it quadratic, and people started learning it that way and they're like, crap, can't fix it now. It's out there, right? Or maybe not. Why quad for 2? Anyone? You know the answer. It does not grow exponentially, actually. What's another way to say it? Instead of x to the second power, what else could you call it? X squared. X squared. So this comes from the polygon that has 4 sides that are all equal, called the square. Okay? And the square, because it has 4 sides, this became associated with a square. And x squared then gave you the area of that 4-sided square. So it was intimately associated with a square which had 4 sides. So that's why we called it a quadratic. Okay? Now you could also classify polynomials not by their degree. Degree 1, linear. Degree 2, quadratic. Kind of makes sense now. But you could also classify polynomials by the number of terms they have, right? So if you have something of the form mx plus b, that is 2 terms, you could also call that a what? A binomial would be a specific polynomial with 2 terms. If you just had the mx part, that would still be a first-degree polynomial, but if the y-intercept were 0, now 1 term would be a monomial, right? So what do you call a Sarah with 1 horn? A monosera. A polynomial with 1 term is a mononomial. No, just a monomial. And what if you just had a constant? What if the mx was gone? What would be the degree of a constant if there is no x? Could you actually put like y equals c? Yeah, it would graph as a horizontal line. What would be the x implied there if it's not there? X to the what power? 0. Yeah. And that works because anything to the 0 power is 1. So that's the same as y equals c. This would be a 0-degree polynomial, and it would also be a monomial. So you have a 0 degree, a first degree, and a second degree. You have a constant, linear, and quadratic. You also have a monomial, a binomial, and a trinomial. Okay, now let's imagine that there was a class that came next called Algebra 3, which is kind of like college algebra, and kind of what we're doing as well. In Algebra 3, you can imagine that you're studying polynomials of this form. ax cubed plus bx squared plus cx to the first plus dx to the 0, or just d. Okay? So what do you think you would call that type of polynomial classified by its degree? We had degree 1, linear, degree 2, quadratic. This would be degree 3, and we would call it a cubic. Yeah, so you could call it a cubic polynomial. Now, if you classify by the number of terms, we had monomial, binomial, trinomial. This one has 1, 2, 3, 4 terms, so it would be a what nomial? Polynomial. Good. We typically, after trinomial, just start calling it a 4-termed polynomial, a 5-termed polynomial, or just a polynomial. Okay, now what's kind of funny if you think about it, poly again means what? Many. Many terms. How many terms does a monomial have? 1. Is it still a polynomial? With 1 term? So according to the definition, 1 is many? Is 1 many? Is 1 many? It's more than 0. Very good. If you compare it to somebody who has absolutely nothing, then having 1 could be many compared to having none. So yes, 1 can be many. Very good. Very good. Be grateful for what you have. That's all I'm saying. All right. Okay, so in Algebra 4, whatever, in Algebra 4 maybe you would be studying polynomials of degree 4. And guess what you call a degree 4 polynomial? You had linear, quadratic, cubic, a degree 4 then would be a 4th degree polynomial would be fine. You can always call it an nth degree polynomial. Degree 1 polynomial, degree 2. But a 4th degree polynomial, would it be a quadratic? Because quad means 2 now? No. We would call it a quartic. A quartic. And a 5th degree would be a quintic. And a 6th degree would be a 6th degree polynomial. Yeah, once you get past quintic, then it gets a little bit difficult, right? Because when you get to 6, then you have to start saying sex, and that's not really good in high school, right? So we just call it a 6th degree polynomial. Yeah. All right. So we stop at quintic. All right. So are y'all ready to define what a polynomial is now for real? Yeah. Here we go. The formal definition of a polynomial function. A polynomial function is, first and foremost, surprise, surprise, a function, right? That means for every input, there's how many outputs? No more than one. And the graph would pass a vertical line test. This must be important. It's underlined. Whose domain is all real numbers. Okay, quick trivia question. Jason, what's the domain of a polynomial? What's the domain of a polynomial? All real numbers. 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 Strotman, give me a type of function whose domain is all real numbers. Polynomial. Excellent. Excellent. When is the domain all real numbers? All the time. 24/7, 365, 366 in a leap year. When's the next leap year? 2020. 2020. Was this year a leap year? Yeah. Did you spend your extra day wisely? Probably not. Yeah. Was 2012 a leap year? Yeah. Was 2008 a leap year? Yeah. Was 2004 a leap year? Yeah. Was 2000 a leap year? No. Who said no? How'd you know that? It's not. It's not. Not every 4 years is a leap year. Yeah, if it's divisible by 100, it's not a leap year. Because there's actually 365.25 something, okay, days in a year. So we have to add an extra day every 4 years, but then we're like, oh, wait, we don't want to over-correct, so we'll kind of back it off every once in a while, you know. And so if it's divisible by 100, it's not. So anyway. Yeah. All right. They used to have the Winter and the Summer Olympics same 4 years. So in one season you have Summer and Olympic, then you have to wait 4 years again. But then they're like, hey, why don't we stagger them? And it worked out nice. Okay, nicely. What's the domain of a polynomial without looking? All real numbers. Good. Okay. That can be written in the following form. Now this is perhaps a little bit more important. F of x equals, how do we read this? It's a subscript, so a sub n is how we read that. A sub n times x to the nth power. So n is actually an exponent. N is just a subscript. It's just something that lays claim to this a. Now n is going to be the degree. It's going to be the degree of the polynomial. Okay? This number in front is called the what? The what efficient? Coefficient. And so we're saying that this a is the coefficient of x to the n, but the subscript n just means that it's associated with the nth power, okay? So then we would have to work down from there. Now I want you to see if you can identify the pattern before I give it to you, and maybe I should have done this first. What do you notice about all of those many-termed polynomials? What would make a polynomial polynomial? A constant, a linear, a quadratic, and a cubic, maybe even a quartic. What do they all have in common? What feature do they have that you can group together? What? What? Oh, good. They're all written in descending order. That's kind of nice. Descending order of what? Degree, right? So if you look at the cubic, we're starting with the 3. The next one down is not 2.5, is it? Yeah, it's one smaller, one smaller, one smaller. So that has something to do with it, that the powers have to be one whole unit away from each other. But what about 2.5 and 3.5 and 4.5? You think that would work? They're 1 unit apart from each other. What else do you notice about these functions? Look at the exponents. What types of numbers are the exponents? What? Whole numbers. Very good. You have x to the 0, which would be a constant, x to the first, second, third, fourth. Those are your whole numbers. And that, along with having a domain of what? All real numbers, are the two most important distinguishing characteristics of a many-termed function called a polynomial. Okay? The exponents on the variables have to be what types of numbers? Whole numbers. And the domain is what? All real numbers. Good. So once we know that n is a whole number that represents the largest exponent, it's the degree. Then we count down by 1. So what would be 1 smaller than n? N minus 1. So that's your next exponent. And the coefficient of then the x to the n minus first term would be some number with a subscript n minus 1. So it means that number is associated with that exponent. And you can continue that process all the way down. If I were to write another one here, it would be plus. What would be next after n minus 1? It would be x to the n minus 2th power, right? And the coefficient would then be a subscript n minus 2. And you can keep going. Plus a sub n minus 3, x to the n minus 3, plus. But at some point, you're going to do this. Plus, yada, yada, yada. So on and so forth. And what are those 3 dots actually? Ellipsis points. Good. It just means the process continues down to plus. You're eventually going to get down to the whole numbers in descending order, 2, 1, and of course 0. So we have a sub 2x squared, a sub 1x to the first, and a sub 0 would be then x to the 0. But we don't need to write x to the 0 because it's what? 1. All right? So we write it in descending order. Now, if n happens to be 2, then this would just be 2, then 1, then 0. If n happens to be 1, then we would just have these two terms, 1 and 0. And if n happens to be 0, then we just have a constant. But if we have like n equaling 57, then the leading term would be something x to the 57th, and possibly then we can have any number of terms smaller than 57 decreasing by 1. Okay, cool. When it is written as we have been writing these, we call it standard form. And how have we been writing them? Tate, you said it. Descending order. Descending order. Or you could say descending degree, or you could say descending order of degree. It doesn't matter. Order doesn't mean just arrangement in this case. We can actually use the word order substituted in for degree. The order of a polynomial is the same as the degree of the polynomial. I don't use it as often, but if you're in HEB and you hear someone talking about the order of a polynomial, they're not like a fast food joint trying to order one. They're talking about its degree. Feel free to jump in on the conversation after today. Okay. What do we call those? If they're written in descending order of degree? Standard form. And that's how you had to write that in Algebra 2 in standard order or standard form in order to use the quadratic formula, right? It was required so you can identify your ABC, which were the coefficients. All right, let's kind of dissect this a little bit and look at the taxonomy of what we had above. Because this type of thing right here is abstract. And maybe you haven't seen something like that before. So the n itself, which is again the largest exponent, it represents the degree or the order of the polynomial. And it has to be a whole number. Okay, it has to be a whole number. That's what this says down here. N has to be an element of the whole number 0, 1, 2, 3. Now, here's a little note. Because the exponents are whole numbers, that is why the domain is all real numbers. And it's underlined and it's all caps, which means it must be important. Does anyone understand why that makes the domain all real numbers if we have whole number exponents? You know how you answer a question like that? You say, okay, what would happen then if we did not have whole number exponents, such as fractional exponents, like x to the 1/2? That becomes the square root of x, and does that have a domain of all real numbers? X has to be greater than or equal to 0. Now, not every fractional exponent, like 1/3, is going to have a domain restriction. Okay, that's still going to be all real numbers. But if it is a fractional exponent, it could possibly lead to domain restrictions. And a polynomial has a domain of what? All real numbers. And that's why it has to have, or that's because the integers have to be whole numbers. Okay, what else? What if it didn't have fractions? What if it didn't have parts of numbers? What if it, we have whole numbers 0, 1, 2, 3. What about if we went the other way? What if we had like x to the negative first? Is that a polynomial term? -1. Hi. Hi. New student. New student. I love the tie. I love the tie. Oh, nice. Hi. Hi. Nice to meet you. Yeah. Where are you from? You're from Texas State. That's down the road. Yeah. Who are you? Are you a math guy? Who are you observing? Yeah. Interns?
Family Consumer Sciences.
Family Consumer Sciences. Is that math?
Kind of.
I see you up here a lot. Family Consumer Sciences. Okay. Well, nice to meet you, Mr. Valdez.
Yeah.
All right. Take care.
Yeah.
Don't let anybody hit you when you turn around.
Yeah.
Yeah. Okay. Bye. Yeah. You too. Okay. Life's all about embracing the awkwardness. All right. X to the negative first is 1 over x, and of course, that means that x can't be 0. So if you have a negative exponent, you have variables in the denominator. And that puts domain restrictions in. So that's why the domain is all real numbers. Because the integers are what types of numbers? Or the exponents are what types of numbers? Whole numbers. That's pretty. I like that. Pretty. Okay, let's go to the next one. How would you read that? Oh, I forgot I recorded that whole thing. It was all recorded. Cool. We read that as a sub I times x to the I power. X sub I times x to the I, if you want to call it that. Yeah. Now, this is kind of the same as a sub n x to the n, but a sub n x to the n is a very specific term in the polynomial, right? It is the largest exponent, so we call that the leading term, and then a sub n will be the leading coefficient. But a sub I, x sub I could represent any term in the polynomial. So like if I were 3, then I would probably be wise for my age. Okay? If I happen to be 3, then this would be a sub 3 x to the third. Okay? If I were 4, then I'd be 1 year older than when I was 3, but we'd have a sub 4 x to the fourth power. Got it? I then is called the what? You can read a lot by learning. This is called the index. You can read a lot by learning. I read that somewhere. Okay. This represents any term of the polynomial, and I is called an index. And all it is it's used to keep track of which term we're on. Now, because it's associated with the exponent I must also be, if you want to put another bullet point, what type of number? A whole number, yeah. But it just keeps track. Now, the reason that we use I as an index is because of this. And I'll show this to you now because first period was asking about it. This is the Greek letter sigma. And maybe you've seen it on Fraternity House or maybe, I don't know, somewhere before. We would write from I equals 0 to, let's say, 4 of a sub I x to the I power. The Greek letter sigma kind of looks like what letter in our alphabet? It looks like a capital E. So, guess what? The Greek letter sigma is standing for their letter what? S. Very good. Yeah, S. Trick question. S. And that's why we call it sigma. Sigma for S. All right? And what it means is why they use S is because sigma is the first letter in the word super cool. But it's also the first letter. That's not even one word. Unless you make it that word because you're nerdy. Got it. Sum. Sum. What's the first letter in the word sum? S, which is the Greek letter what? Sigma. So the way you would read this is you're going to add up all the terms from starting with I equals 0 to 4 represented by this. Okay? So you would just start off by plugging in the 0 for I, and you get a sub 0 x to the 0, plus then you go to the next integer, 1, and you get a sub 1 x to the first plus a sub 2 x squared plus a sub 3 x cubed. Oh my gosh, when do we stop? Plus a sub 4 x to the fourth. Now we stop. Now we stop because this is your upper bound. So what it is, it's a nice condensed way, almost like a computer program that generates terms. Okay? So this would generate a fourth degree polynomial. That's generated by, keep it down, we're trying to learn. Baseball. From heaven. All right. So that's where the index comes from. Let's look at the a sub i's. The a sub i's themselves, that is the numbers in front of the x sub i's, those represent the what efficients? The coefficients. And they can be 0 except the leading term, a sub n. A sub n cannot be 0. Why can a sub n not be 0? Because if a sub n were 0, what happens to this term? It goes away, right? And no longer is the degree n, it's n minus 1. So we're basically going to take the largest term that we see, exponent-wise, and we're going to call that the degree. But behind n, any number smaller than n, the a's sub i's can be 0, which means we don't have to have representative terms. A fifth degree polynomial does not have to have a visible fourth degree, third degree, second degree linear term, constant. Okay? It can, but it doesn't have to. So a sub n is the leading coefficient, and a sub 0, the one with the x to the 0 that's not there, is the constant. X is your independent variable, f of x is your dependent variable, and remember f itself is the name of the function. So you can just refer to it as f, or f of x. Got it? So here's what a polynomial looks like with the numbers plugged in. Now this is not a polynomial function, because it's not equal to f of x or anything. This is a polynomial expression, but same thing. Notice, is it written in descending order? The degree is what? 5, and then the next one, 4, 3, 2, 1, x to the 0 is a constant. Yeah, so we would call this a fifth degree polynomial, or a what? What did I say? You can call it a fifth degree polynomial or quintic. Good. A quintic polynomial. It's a nice word. Quintic polynomial. So that would be classifying it by its degree. It also has 1, 2, 3, 4, 5, 6 terms, so we can call it a what? By terms. A 6-term polynomial, right? Good. Not a sexanomial. No way, that's something different. Now let's talk about the subscripts on the i's. If the degree is 5, then 3 would be your leading coefficient. 3x to the fifth would be your leading term. But 3 would correspond in the rule above as a sub what? 5, because it's associated with the fifth degree term. So 3 would be a sub 5, 6 would be a sub 4, negative 2 would be a sub 3, a sub 2 would be what? Well, a sub 2 would be, what's the coefficient of the x squared term? 1. So a sub 2 would be 1. I switched it there on you. What would a sub 1 be? A sub 1 is the coefficient of the first degree term. It's 7. And what's a sub 0? Negative 6. Okay, so that's how that works. And again, notice the exponents are indeed, in fact, what types of numbers? Whole numbers. Okay, so you think you know what a polynomial looks like by the equation? You think so? Think you can pick a polynomial out of a lineup? It's him, officer. Let's try it. Example 1. Identify each of the following polynomials. Identify each of the polynomials. You just want to squeeze that into everything, right? Identify each of the following polynomials, or the following, Hi. I'm starting over. Let's look at example 1. Identify each of the following as a polynomial p, that makes sense, or not a polynomial n. Be sure to understand why. Okay, I'll be sure. All right, example number A. We had 4x equals 4x squared plus the natural log of 3 times x minus 1. Is it a p polynomial or an n and not a polynomial? I don't know. I don't know what that is. Let's do the first one together. What are we looking for? What makes a polynomial a polynomial? The exponents on the what? On the x's, they've got to be what types of number? Whole numbers. Okay, let's check that out. I have an x squared. 2 is a whole number. I have an x raised to the implied 1 power. 1 is a whole number. And I have a constant, which is going to work because a constant, remember, is just x to the 0 power, which 0 is the smallest whole number. So it meets all that requirement. Now, one thing I didn't emphasize up here, which is worth going back to, your a sub i's, that is your coefficients, your a sub i's can be elements of, it's a weird looking R. We usually write like that. The coefficients themselves can be any types of numbers. They can be whole numbers, they can be integers, they can be rational numbers, fractions. They can even be irrational numbers. Your coefficients can be any real number. What are some irrational numbers? Square root of 3. That's called an algebraic irrational number because it can come from a solution to an algebraic equation. What's the most famous algebraic irrational number? Not square root of 3, but square root of 2. Square root of 2 is the most famous algebraic irrational number. And you can have a coefficient of negative or square root of 2. Did I tell you the story about the square root of 2? I did, right? Earlier in the year when we talked about the Pythagoreans. I did, right? Hypasis. Do you remember Hypasis? Yeah. The Pythagoreans had this credo, this religion, if you will, that everything can be represented as the ratio of 2 integers. Okay? Just like Christians believe that Christ is the Savior. It's kind of the same thing. I don't want to bring up religion, but that's how intensely devout they were to that idea, that everything in the world could be represented as the ratio of 2 integers, and also that you could meet beings. They made you toot. Okay? So that was also part of the religion. All right? And then your soul would escape, right? Yeah. Weirdos. But they did give us the Pythagorean theorem. And their very own Pythagorean theorem crumbled their credo that everything could be expressed as the ratio of 2 integers because Hypasus was doing some number crunching one time while he was sneaking some beans. And he came up with the square root of 2, and he said, you know what, the square root of 2, it can't be represented as the ratio of 2 integers. So he let the group know, and they're like, dude, whoa. And that would be like telling a Christian that Christ is not the Savior, and you have irrefutable proof. That would really shatter your entire existence, right? It would shatter everything, and that's what it did to the Pythagoreans. So what did they do? They're like, hey, Hypasus, don't tell nobody. And he's like, don't tell anybody. I'm like, man, Hypasus, you always doing that, right? He was a stickler. So you know what they did? They said, hey, Hypasus, you want to go fishing this weekend? He's like, I love fishing. Deep sea fishing, even better. So they took him out on the boat, right? And like, you know what? We're going to be in a lot of waves. There's going to be a lot of motion in the boat. Here, why don't you wear these concrete shoes? They'll keep you kind of anchored to the boat so you don't fall over in the boat. It's like, oh, okay. Whatever you say, I like that. And then they're like, hey, Pastor, come look there's a big fish over the side here. And he's like, okay, I'll be there in a minute. And he gets to the side and he leans over, then they dump him. And of course, the insult to injury, his name was what? Hypasus. And you know what they said as they threw him over? They said, hey, Hypasus, bye, Passus. And he's like, that's not funny. And then, of course, he's home. So he's the only guy that I know of in the history of the world that was killed for knowing a number, the square root of 2. Okay? It shattered their existence. You can't keep a good number down, right? I don't know about the square root of 2. You could go preach the square root of 2 at lunch in the Commons, and people are going to think you're weird, but no one's going to take you fishing because of it, okay? So those are called algebraic irrational numbers. We also have transcendental irrational numbers like pi and e and phi, the golden ratio. So the coefficients could be any real number. So if we look up here, it has to pass that test. Is 4 a real number? Yes. And then back to your question, Trevor, is the natural log of 3 a real number? We looked at the graph of the natural log of x this year already, yeah? It has a vertical asymptote on the y-axis, and it lives everywhere to the right. Does 3 live to the right of 0? Yeah, so it's going to be a real number. In fact, it's just a little bit bigger than 1 because the natural log of e is 1, and e is about 2.718. So it's real, and of course 1 is real. So true or false? Polynomial? True. It's a polynomial. Okay? So now we know what we're looking for. Letter B, you do. We got 5 minutes. We got to get through this example. Letter B, you do it. I'm going to give you 30 seconds. P or N? If you finish that one, go on to the next. Okay. I don't know the rest of the song. What is the, it goes boom, boom at the end. Polynomial or N? Let's look at it term by term. It's got to be a real number times x to a whole number power, right? That's the qualifications. 10 is real, 2 is whole. Good. Next one. Negative 11 is real, 3 is whole. Next one. Ah! 3 is real, x is whole. What? That one looks a little different. This one's flipped. Instead of having a variable base and a whole number exponent, it has a whole number base and a variable exponent. Does that look like a polynomial term? No, it's not. So the first two are polynomial terms, but taken all together, he ruins it. There's some kind of hybrid there. In fact, this belongs to what family of functions? Exponential. Good. It's an exponential. So it's not a polynomial. All right, letter C. Or let's highlight why it's not. Why I circled it. There he is. He's the culprit. This one, polynomial or not a polynomial? No, why not? We got a 2/3. 2/3. What about this -2 over here? He calls it a problem? We're looking for the variables exponents, right? Or the exponents on the variables. That's an exponent that's negative, which is not allowed if it were attached to a variable. Is 9 a variable, though? No, it's called 9. So 9 to the negative second, remember, is really 1 over 9 to the positive second, which is really what? 1/81. So that's a constant. It's okay. So you have to make sure you're looking for exponents on variables. All right, so that's a no. How about this one? Letter D. Yes? Is it in our standard polynomial form? No. How could we get it into standard polynomial form? Distribute 2x cubed minus 3x squared. Now you can analyze it in that form. 2 is real, 3 is whole, -3 is real, 2 is whole. Welcome to the club, Mr. P. A, B, C, D, D comes next when you don't know the alphabet. I have 2 Ds. Oh well. Polynomial, yes or no? Let me help you out. There's an x, whole number, 1 is real. There's an x, whole number 1, real, right? -7. There's an x, whole number 2, 4 is real. Ah, very good. Yeah, very good. You can't just look at the x's wherever they happen to be, right? You have to put it in the form, which means the x's have to be in the numerator. So if you rewrite the first term, it would be 4x to the -2th power. And can we have negative exponents on a variable to be a polynomial? No. All right. How about E? Go term by term. Is pi real? Oh, yeah. It's also delicious. X cubed. Is 3 whole? Yeah. So first term's good. 7's real. X to the first is whole. Good. Plus, is E real? It is. I said it was earlier. It still is. It's 2.718. And so it's real. It's transcendental irrational. 2 is whole. And the natural log of 1, is it a whole number? There's no variable. Is it real? Is it a constant? Yeah. In fact, what is the natural log of 1? That's one you should know. If you think of the graph of the natural log of x, where does it cross the x-axis? At x equals 1. The natural log of 1 is 0. So really that term's not even there. Remember, the natural log has to be taken up as any positive number. So as long as it's the natural log of a positive number, it's a constant, it's good. So this one is yes. All right, let's finish up the last two. What about this one? No, because that's x to the 1/2 and x to the 1/3. So this one doesn't have any terms that are polynomial. That's a no. We can call that one a no-no, right? No-no. I don't think so. A, B, C, D, D, E, F, G. All right, this one, last one. Let's see, if I simplify that, I get x squared If I simplify that one, I get 2x to the second. If I simplify that one, I get x. And then pi to the 0, that's just 1, right? And then I can combine like terms and I get 3x squared plus x plus 1. Right? I simplify the first term, get x squared. I bring the negative 2 to the top and get x to the positive 2's. And then something squared is itself plus 1. And it simplifies, so is 3x squared plus x plus 1 a polynomial? Hey, when do we find the domain? Before or after we simplify? Before. We've learned that lesson. So it simplifies down to a polynomial, but right here, x can't be 0. And right here, x has to be greater than or equal to 0. Does this thing have a domain of all real numbers? No! So it's not a polynomial. We'll pick up with example due tomorrow. Have a good day. You are off to a great start. See you at the pep rally tonight.